Second of the two preliminary design teams. So now we have Pelican Systems. I'm going to turn it over to Sal Cardenas, and you will take it.
Thank you, Professor Halpern. Good morning, everyone, and welcome to Pelican Systems Preliminary Design Review. I am Sal Cardenas. I am the design team lead, and here's our Pelican Systems team. First, we have Alexander Moritz, Alexander Keel, Stephen Hocking, Jacob Heileman, Anna Warren, Philip Rick, Timber Aguilar, Bryce Libertone, and Grace Brennan, who is our sub-design team lead. So first, I will start off with our initial requirements that were given to us by Professor Halpern. We had to be a sea or land-based aircraft that could be capable of rail launch for the sea-based operations for the Coast Guard, and be assembled from a transport container of 3 foot by 3 foot by 6 foot. They also had to be able to launch and climb to an altitude of 1,000 feet, and perform search and rescue and border security operations to be able to identify and recognize an average male. So our derived requirements, or our CONOPS, are our aircraft had to be waterproof since it did have to do sea-based missions. It also had to be all electric, battery powered for our propulsion system, and be easy to manufacture to be cost efficient. And it also had to transmit all this data to the ground station either on the land-based mission or the patrol cutter of the Coast Guard. So here's a preview of our land-based configuration. As you can see, we have a 150-foot-inch wingspan, or 12.5 feet. Our total length is about 78 inches, and our height is about 34 inches. And here's a preview of our sea-based configuration. As you can see here, the pontoon floats that are installed, where it would perform a water landing in a sea state of around 2 or lower. And here is similar aircraft to our Seabird. We have the Scan Eagle, which is currently being used by the Coast Guard on patrol cutters, and it is a rail launch capable vehicle. And here's the Penguin BE, which is all electric, just like the Seabird. And here's the Skylight, which is also a rail launch capable aircraft they use for land-based missions. And here's a preview of our mission profile for the land-based operations. As you can see, we have a loading time of 2 hours. And here's a preview of our sea-based mission profile. And Bryce Libertone will go into more detail in his section. And next we have Alexander Moritz with Payload Systems.
Thank you, Tom. Good morning. Today I will be going over the payload system of the Seabird. The payload system is a primary design driver. Without it, the Seabird is not able to perform its mission. And with this in mind, first I will go over the current configuration, next the hardware element, and finally the operation of the payload. The Seabird has 2 missions, board patrol and search and rescue. Both of these missions have the common goal of human target location at water. The payload must be able to detect a person using an infrared system and recognize a person using an electro-optical system. Detection consists of being able to find something on an image, and recognition consists of being able to tell what that something is. The solution found was a multispectral camera mounted on a roll-tilt mount. The other requirements that drove this selection were pixel requirements and target size requirements derived from the Johnson criteria. This is how the payload will sit at the nose of the aircraft. It will sit behind a clear shield. The material hasn't been determined yet, but we are looking into optical grade plexiglass and polycarbonate. This will be determined in the detailed design phase with testing for durability and image distortion. This is a summary of how the hardware will be laid out, the focus being the camera. The Hawk EM246 is capable of capturing imagery in the visible to near infrared range, sufficient to fulfill our mission requirements. And it will be mounted along the centerline of the fuselage, shown by the dashed line. The field of regard is defined as the angular limits relative to camera placement and obstructions. So we have 45 degrees visibility in the XC plane and 90 degrees on the YZ plane. The seabird operator will be the one who will monitor the feed and control the tilt and rotation of the camera. And the payload and comm systems will be powered by separate batteries. This will be covered in the next section by Alexander Keel in Autopilot and Communication Systems. And in conclusion, the hardware selection is predicted to meet mission requirements, and the payload will be controlled by the flight computer, and we will be determining the clear shield in the detailed design phase. Next is Alex Keel with Autopilot and Communication Systems.
So, I'll be discussing the components in the Autopilot and Communication Systems and how the relevant requirements of operating at 5 nautical mile range may influence these choices. I will conclude the section with how we intend to power all the onboard electronics. First, the Autopilot that we will be using is the 3DR, or the APM 2.6 and 3D robotics. It is a common platform used in a lot of small personal UAV systems. It typically runs the ERAU-plane firmware and contains a barometer, a barometric altitude sensor, and a 3-axis gyroscope attitude sensor. But it is an incomplete Autopilot implementation. It requires an external compass and GPS unit, which is intentionally built for the APM 2.6, and an airspeed sensor, also intentionally built for the system. The transceiver that we'll be using is the XB900 Pro. There will be 4 of these units, 2 for the payload and 2 for the Autopilot. It's capable of operating at almost a 5.5 nautical mile range, which exceeds the 5 nautical mile range imposed by our RFP. On board, we'll be using a small duck style antenna, which will provide 2 decibels of gain. But because it will be located along with all the other electronics, as seen in Philip Braggs' weight balance section. On the ground station, we will be using a much larger Yagi-style directional antenna, which will provide 14 decibels of gain, and additional gain will be provided from a power amplifier. The human interface on the ground control station will be Mission Planner. It is typically used with the ERAU-plane Autopilot firmware. This is an example of it being used to set up a grid flight path, which is applicable to Bryce Libertone and search patterns. We'll just simply be using a notebook PC for the ground control station. Hopefully we will be able to integrate with some type of Coast Guard system in the future. Now, one issue that we had to resolve was how to power all of the onboard electronics, because the batteries used for the rotor do not have enough of a reserve to power the electronics. This table shows the components that will require power, the number of the components, and their anticipated draw, which sum to 36 watts. Knowing that we have to operate for about approximately 2.2 hours from Bryce Libertone's mission performance, 80 watt hours of energy are required. With that, a battery was selected. It provides 85 watt hours of energy and is a 4-cell lithium polymer pack. Because of the 4.8 volts, the 4.8 volts exceeds the voltage which may be introduced to any component in the system, so some sort of regulator will be necessary. So in conclusion, our range should exceed 5 nautical miles, and we are predicting a signal to noise ratio of 35 decibels at that range. Next, Stephen Hawking will discuss the initial design envelope.
Thank you, Alex. The initial design envelope was used to calculate initial estimates for wing platform area and engine power required. To do this, we can analyze various flight conditions and then created an overlay plot of wing loading versus power loading. The conditions analyzed were stall, takeoff, landing, cruise, and a 2.5 G turn. Each of these conditions has associated equations from the Roscom text, and for some of those equations, certain values need to be estimated as they have not been determined since this was the beginning of the design process. These are some of the initial values. The aspect ratio, cruise, and stall velocities were selected based on the similar systems that were previously shown. The swath width is that which is based on the calculations from the payload section, and a 20% overlap is included in this to calculate our minimum turn radius during our search patterns. The CL max of 1.3 is based on our airfoil choice of the GOE 398, and the flight altitude density is the hot day density of 1,000 feet for worst case scenario. After these values, along with a few others, were put into the Roscoe equations for the various flight conditions, an overlay plot of wing loading versus power loading was created. As you can see from the plot, our limiting conditions are takeoff and stall. Takeoff is one of our limiting factors because of our requirement to take off from a gravel runway. It's a very high coefficient of friction, requiring a lot of engine power. From this overlay plot, we selected a design point that maximized wing loading and applied a 5% growth factor to get the current design point. From that design point, the wing loading and power loadings are listed on the slide above, and then using the maximum allowable weight of 30 pounds, we were able to calculate initial estimates for wing planform area and engine power required. These values were then passed on to aerodynamics and power requirements to provide them with a starting point to be iterated upon until we came up with what we currently have. Up next is Jacob Heilman with aerodynamics.
Thank you, Stephen. We'll be going over our selected values, our total lift coefficient, our just a brief process of our Raymer's component drag buildup method, our parasitic drag, and then our drag polar, and our range and endurance plots, and then our trim angles of attack. Using an iterative design process and taking the initial values as Stephen Hawking's initial flight envelope, we can determine final predicted values of an aspect ratio of 9.18, a platform area of 17 feet squared, and maintaining our wingspan of 12.5 feet. To develop our total lift curve slope of our aircraft, initially we have our wing body slope here in the dotted line, which is developed by converting 2D data, the GOE airfoil 398, as listed in macro report 331. Further, to get the total CL, we consider the negative lift produced by the tail, thus reducing the overall lift of the aircraft, the whole angle attack. Therefore, we now predicted L/D max, CL max at 1.3 at an angle attack of 14 degrees. We use the Raymer's component drag buildup method, which uses form factor, skin friction, and interference components in the main components of the aircraft. We consider miscellaneous drags as fuselage and pontoon upsweep with cooling drag and a perturbance of 10% of the overall parasitic drag. Here's our land-based configuration, parasitic drag. As you can see here, we have a overall parasitic drag of 0.20295, with the main component being the wing. This is due to a large platform area with an airfoil thickness of 14%, driving up our wetted area and thus our drag. The second largest is our land-based landing gear. This is due to a non-aerodynamic design for strength purposes. Next is our sea-based parasitic drag at a value of 0.0248, with our main component again being the wing at 44%. And our second largest component is our sea-based landing gear, due to two pontoons being close to the fuselage and increasing our interference factor of the aircraft. Here's our drag polar. As you can see, they're very similar for both configurations. There's a characteristic drag bucket, and this data was then used to create our range and endurance plots. Here's our range plot. As you can see, our sea-based configuration has an increased L/D max, and both of these values were used to size our battery for the cruise phase of the mission. Here's our endurance plot. Again, you can see an increased maximum endurance parameter for our sea-based configuration, and these maximum values were used to develop our battery size for our loiter phase of the mission in power requirements analysis. Here's for the various states of our LRD max was used to produce, was shown with occurs at a CL of 0.61, which occurs at an angle of attack of 2 degrees. Our sea-based maximum endurance parameter occurs at a CL of 0.73, which occurs at an angle of attack of 4 degrees. And our land-based maximum endurance parameter occurs at a CL of 0.85, which occurs at an angle of attack of 6 degrees. In conclusion, these values will be passed on as input for our power requirements analysis and our S&C calculations. Next up is Hannah Warren with power requirements analysis.
Thank you, Jacob. Today we'll be discussing how we determine our power requirements and use those power requirements to determine our propeller, motor, and electronic speed controller selection. The first step was to evaluate the power requirement. The first step was the thrust, which is equal to the drag during straight, level, unaccelerated flight. So we took the CL required to fly over a range of velocities and used the drag polar to find the corresponding drag coefficient to develop the thrust required plot. The point of minimum thrust corresponds to CL over CE max, which is the cruise condition. So we defined a cruise velocity of 31.6 knots for both configurations. Next, the power is the thrust times the velocity, which we developed into a plot here. And you can see the point of minimum thrust corresponds to CL over 3000 or CE max, which defines our loiter speed, which was found to be 28.6 knots for both configurations. All of this was evaluated based off of a 30-pound aircraft on a hot day. We chose 30 pounds even though we're under 30 pounds to give us a conservative estimate. You can see here our selected motor provides a power available of 3.3 horsepower with the efficiency for cruise. We selected our motor based off of our takeoff requirement, which was more constrictive than our loiter requirement because we had to take off of a gravel runway. We chose the KDS brushless 3725 motor. It has an uninstalled horsepower of 5.9 horsepower and it's very lightweight. We chose this even though we seem to be overpowered at this point because there was questions on whether or not smaller motors could actually move the size propeller that we needed. We chose the electronic speed controller based on the max amperage of this motor, which was 100 amps. Thus, we chose the Phoenix Edge HV120 electronic speed controller. It's lightweight and fully programmable, which will aid in interface with the Autopilot. We chose our propeller based off of some experimental data provided by Professor Helwin. We chose it based off of the maximum propeller diameter that we could move, which was 17 inches based off of maintaining a 15-degree tip-back requirement so that our aircraft could roll on takeoff. We chose it based off of its efficiency during loiter, since we have a 2-hour endurance requirement, which drives our battery, which is a very heavy component. We chose the ABC 17x10 C2 propeller. This exact propeller is not actually commercially available anymore. However, most of the 17x10 propellers have very similar performance, and they are very low cost, so it will not be cost prohibitive in the future to buy several propellers and evaluate them and choose the best one. For the battery selection, first we had to determine the amount of energy required for each phase of flight. We did this by taking the power for each phase and multiplying it by the time for that phase, which will be further discussed in Bryce Lopertone's mission performance section. And adding all of these together, we get a total capacity of just over 25,000 milliamp hours for the land-based configuration and just over 23,000 milliamp hours for the sea-based configuration. We chose an Amacell custom high energy density lithium polymer battery in a 12S2P setup, which is basically a 12 series cell and then 2 parallel packs to get the desired capacity. They provide a total capacity of 25,200 milliamp hours, which is above the capacity required for the land-based configuration, which obviously required more power than the sea-based configuration. And it has a total weight of only 10.4 pounds, which is very important for us to stay under our 30-pound weight limit. In conclusion, we have developed the power requirements to find a loiter and cruise velocity and chose a motor which will provide us enough power for takeoff, a propeller which will provide sufficient thrust, and a battery which will provide sufficient capacity to complete our mission. Next will be Phil Wright with weight and balance.
Thank you, Hannah. I'll be going over the weight and balance of the sea-based, both the land and sea-based configurations. I'll be going over our overall CG of the land and sea-based configurations and go over our mass moments inertia that lead into stability control. For our weight, we divide it into 4 categories: the structures, the fixed equipment, payload, and propulsion. We pick these based on our mission requirements to best meet them. Our payloads in the front to provide our best field of view and field of regard. Our propulsion systems in the back be a pusher propeller to not obstruct our field of view. And our batteries in the main under the wing, where our fixed equipment is in the main fuselage for transmitted issues. Here's a breakdown of our weight by component. Our structures component was estimated from the structures component, later defined into the irregular structure section. Our heaviest component is our wing at 3.51 pounds. For our sea-based configuration, our floats replace our main landing gear at 3/4 of a pound over our main landing gear of 0.84 pounds. Our heaviest component of the aircraft is our battery, as mentioned in Hannah Warren's propulsion section, of 10.4 pounds. This is both our weight and CG driver, so much was done to optimize with respect to the weight for this. Adding those weights up, we ended up with an uninstalled weight of 22 pounds, just over 22 pounds. Our overall installed weight, adding a 30% installation factor via Professor Helbling's recommendation, was 28.8 pounds. This is predicted to be under our 30 pounds of max allowable weight for our RFP requirements. Our speed base is actually under our land-based configuration at 26.68 pounds. For our center of gravity, we took the moment contributions from each individual center of gravity components. As you can see here, the X components are on the top row and the Z components are on the bottom row. The data we took was about the nose of the aircraft and the bottom of the landing gear. You may notice that we have a little bit of an incidence over there. This has better helped our takeoff requirement. Our XCG ended up being about 18.3 pounds, which is right underneath the wing. This is later defined in the stability control section. This is being able to be iterated upon. Our battery is on a track system to be able to vary the CG. The limits of this will also be defined later on in the stability control section via our static margin. Our ZCG is close to the center line of the aircraft, therefore we have very later defined the maximum use of inertia. For our sea-based configuration, this is not too dissimilar from our land-based configuration. Our ZCG is closer to the center line of the aircraft, and our overall ZCG is actually 18.2, which is close to the overall configuration. As mentioned, the battery is on a movable track to vary the overall CG to iterate to a proper location. For our mass moments of inertia, this translates resistance to motion about a particular axis of the aircraft. Our y-axis is our biggest mass moment of inertia. This translates to our pitching motion. Therefore, we have our hard takeoff requirement about the pitch axis. Therefore, our control surface of our elevator will be appropriately sized to make sure we have proper pitch authority. Our lowest mass moment of inertia, I said here, is about our z-axis. This means we are most susceptible to yaw motion. Therefore, our rotor will be appropriately sized to make sure we meet our crosswind component that are defined in this stability control section. In conclusion, we are predicted to meet our 30 pounds max allowable takeoff weight. Our center of gravity is in a good location to provide stable aircraft that are defined in the stability control section, control services. I'll be now going over our stability control analysis from the Seabird. I'll be talking to you about the stability, the static stability, the control surface sizing, and the dynamic stability of the Seabird. The axis system we chose for the Seabird is different from the weight balance. It is a body-centered. X out the Y front of the nose, Z down, and Y out the right wing. For our static stability derivatives, we estimated these from Jake Heilman's aerodynamic section, which are trends of lift, moment, and drag. We were then able to calculate our overall static margin to be 0.15. This was chosen and iterated upon to make sure we have good static stability as well as dynamic stability to meet our takeoff requirements for our pitch. We then calculated our roll, pitch, and yaw moments about the axis of the aircraft. By definition, we are predicted to be stable about this aircraft. We will later define the section after we do wind tunnel testing. They'll give us better trends of lift, moment, and drag about after we do wind tunnel testing. For our control surface sizing, as said, we base these off our mass moments inertia to meet certain mil spec requirements. For our bank requirements, this is required to meet at 1.7 degrees of seconds to bank per mil spec 17. Our max deflection was 20 degrees. We were able to meet this in 1.07 seconds, and even at a 75% max deflection of our ailerons, we were able to meet this in 1.39 seconds. We made a 1 degree of freedom time response of these to check, to verify it dynamically that we were able to meet these requirements. Here are trends of our time response. As you can see, with a 15 degree of deflection, we were able to meet our mil spec requirement of 1.7 degrees of bank. For a rudder, as mentioned, our mass moment inertia about the y-axis is the most susceptible to crosswinds. We're required to meet a 10-knot crosswind. We meet this in 10.3 knots with a little help from our aileron deflection. Our rudder is 62% of our chord, therefore we have a high moment about the y-axis to make sure we meet our requirements. For our elevator, our, as said before, our pitch requirement is our hardest requirement to meet. We added a little incidence on our takeoff and for a gravel runway. Therefore, our elevator is 57% of the core to make sure we have good pitch authority. Our max deflection of 20 degrees, we are able to meet our pitch control requirements in 5 degrees, actually our max elevator deflection to make sure we have good pitch authority. We're also required to meet a 2.5 G turn. We're able to meet this with a max deflection of 7.5 degrees in the elevator. For our dynamic stability model, we used classic control theory to develop a full state feedback system. We took our static stability derivatives, put it in a state space form. We were able to determine the transfer functions via pilot input of our Seabird. We then were able to estimate our poles of the system. Our longitudinal are in the diamond. We have our phugoid and our short period. Our short period is close to the right half plane, which is unstable. We'll later evaluate once we do wind tunnel testing to make sure that we are dynamically stable. We are predicted to be dynamically stable right now. We'll also explore the effects of adding a gain system and a compensator. We'll use gain compensation to see if we can move those short period poles more to the left half plane to be more stable. Our ladder directional includes the roll, the Dutch roll, and the spiral. The roll is stable, the Dutch roll is predicted to be stable, and our spiral is stable, which is often unstable for most aircraft. Since we have a box tail for the aircraft, we don't predict that we'll be unstable about spin axis or spin. So we don't expect those to change much, and we do not have, as you can see, our box tail, we do not have a lot of coupling of aileron and elevator rudder deflection. In conclusion, we are predicted to be statically and dynamically stable. Our control surface sizes are appropriately sized to our mass moment of inertias. And we have a dynamic stability model, which we will later evaluate after wind tunnel testing to see if we are dynamically stable. I'll now pass it off to Timmy Agler for our structure section.
Thank you, Phil. So today I'm going to be going over the fuselage, wing, and empennage structural arrangement along with the wing. I just want to note that all configurations are initially assumed and will be further evaluated in the detail phase next semester. So for our fuselage arrangement, we will have 6 bulkheads, one located right at the nose, where the payload system is going to be located. We'll have one right in front of the wing, 2 under the wing, then 2 after the wing. We'll have a floor running the span, here as shown in this diagram, and we'll have 2 longerons as pointed out here. This is assumed to be a 4-ply carbon fiber E-glass with a quasi-isotropic layout. The skin of the fuselage will be a 2-ply E-glass with a plus/minus 45-degree layout schedule. Again, these are assumed values and will be further analyzed in the detail phase. For the wing arrangement, we'll have 2 spars. The main spar will have a diameter of 1.41 inches and will be located 3.11 inches aft of the leading edge. That's the thickest part of the airfoil. The second spar will be located 3 inches aft of the main spar and will have a diameter of 0.91 inches. The spars themselves are assumed to be a carbon fiber hollow tube. There will be a total of 34 ribs placed within the 12.5-foot span of the wing, and they'll have a spacing of 4.41 inches as shown here. The ribs themselves are assumed to be a 2-ply E-glass with a plus/minus 45-degree layout schedule. The skin itself is a single-ply E-glass with a plus/minus 45-degree layout schedule. Again, this will be reevaluated in detail. For the horizontal structure, we will have 5 ribs placed within the span with a spacing of 6.13 inches. The ribs will be 2-ply E-glass with a plus/minus 45-degree layout schedule, and the skin itself will be a single-ply E-glass with a plus/minus 45-degree layout schedule. There will be 1 spar along the span of the horizontal tail, and will be located 4 inches after the leading edge, and will have a diameter of 1.25 inches. This will be a hollow carbon fiber tube. For the vertical tail, there will be 4 ribs placed evenly spaced at 4.33 inches and will be made out of the same material as the horizontal tail, the E-glass, 2-ply E-glass for the ribs and a single-ply E-glass for the skin. There will be 1 spar going the span of the vertical tail as shown. Will have a diameter of 3/4 of an inch and is going to be a hollow carbon fiber tube. It will be located 2.3 inches aft of the leading edge and follow the same sweep as the leading edge. The landing gear was also analyzed in the ANSYS workbench. We have a 120-pound load applied here as shown. The 120-pound load was determined by taking the max weight of 30 pounds, multiplying that by a factor of safety of 1.5, and multiplying that by the CFR 23 value of 2.67. The CFR value was used since there were no initial recommendations for a small UAS. Therefore, the CFR 23 was used. So it was suggested by Professor Helding that the landing gear itself not deflect more than 1 inch. And as you can see on the one side here, it is less than half an inch, so total deflection for the main landing gear will be less than an inch as suggested by Professor Helding. The landing gear itself is going to be a carbon fiber, and it has a yield strength of 100 KSI. And as you can see here, this is below the yield strength of the carbon fiber. So the nose gear was also analyzed. This is a picture of the nose gear right here, and this section is what is being modeled here. The 120-pound load was also applied. As you can see, we also are under the yield stress of 100 KSI. The fork strut was also analyzed in the ANSYS workbench, and this part right here where the wheel attaches, and had the same amount of load applied here as can be shown, and has a max stresses here, and will be under the 100 KSI of the carbon fiber. So in conclusion, we'll have a total of 6 bulkheads, 34 ribs, 4 ribs for the vertical tail, 5 for the horizontal tail, and the landing gear is also analyzed. Again, these will be evaluated in the detailed phase, as these are just initial assumptions given by Professor. So for mission performance analysis, here's Bryce.
Thank you, Zipper. I'll be going over the mission performance analysis. I will be going over the mission profile in our support section. For the mission profile, I will go into detail about the takeoff, the climb, cruise out, loiter, cruise back, or descent, and our landing. This is a side view of our land-based profile. Included are the times for each individual section. Here is the top view of the land-based profile. As you can see, we will take off from a ground runway, having a takeoff distance of 450 feet, taking a time of 12 seconds. We will then climb to an altitude of 1,000 feet, cruise out to our loiter area, which is a grid-like pattern, which will be predetermined as of the border patrol. We will then cruise back to our descent area, descent to landing on the same runway. We will land in 745 feet and take a time of 23 seconds. At this time, this distance is above our required 500 feet, but we plan on accounting for that with our ailerons and hopefully increasing our drag. Here's a side view of our sea-based mission. The main key differences is our rail launch and our water landing and the times it takes to do both. This is the top view of our sea-based water landing. We will be launching from a Coast Guard cutter. The rail launch, which will be defined in Stephen Hawking's control section later on. The total distance will take 20 feet, take a time of 5 seconds to take off. We will then climb to 1,000 feet, cruise out to our loiter area, which this time will be a spiral out pattern with an increasing radius, and then until we locate our intended target. Once we have located our intended target, we will then cruise back out to our desired descent area, land in water, which will take less than 50 feet in less than 15 seconds, which then a Coast Guard Zodiac will come out and collect the seabird. For our support sections, I will go over our reliability, our maintainability, our spare parts, and our transportation. For our reliability, we use the durability of 5,000 flight hours given to us by Gunlock. We will then use a number of failure per 1 million flight hours given to us by Austin to get a mean time before failure for each component listed here. For our maintainability, we will have maintenance personnel present for each mission. The maintenance personnel will have easy accessibility through a hatch in the nose of the seabird for pre and post-op mission checks. And the personnel will also be given a manual for a time for overhaul for each component as listed before. Here's a list of our spare parts. Ones that we would like to point out would be an extra battery, extra antenna, and a basic toolkit to ensure that the seabird can perform its mission. All of these parts will be transported separately from the actual seabird. The seabird will actually be transported in a 3x3x6 box. You have the wings here on the sides, both landing gear underneath, with the fuselage in the middle and the empennage in the rear. So it's being that everything is in one box, either mission can be performed. So in conclusion, we are predicted to take off in less than 500 feet, We will be able to climb to an altitude of 1,000 feet. We have 2 sets of ordering conditions, able to rail launch and land in water. And for our support systems, we will have maintenance personnel, extra spare parts, and then we will be able to transport in a 3x36 box. Next is Stephen Hawking with our control section.
Thank you, Bryce. Control consists of the elements that are required to control the system. These consist of the portable equipment, human interface, security, and launch and recovery. The portable equipment consists of the ground station, both the computer and the antenna, as previously discussed, along with an RC transmitter that will be used for manual flight when the system is within visual range of the operator, and also for takeoff and landing. Another part of the portable equipment is the rail system. We have selected the UAV system rail launch system, as it is capable of launching systems up to 77 pounds and at velocities up to 44 knots, both of which are far above what is required for our system of just under 30 pounds and a velocity of approximately 30 knots. The carriage is fully customizable at the factory, so we can have it built to fit our system specifically, and it comes with the air compressor, control box, and a storage box needed to operate the rail. The final part of portable equipment is the support equipment, as previously discussed. Moving on to human interface, this is how the human operator will interface and control the system, and it's going to consist of the Autopilot system. An example of what will be displayed on the Autopilot screen is listed above. Flight data, a map to show the flight path, and an artificial horizon. Now, this is a fully customizable system, so a window could be put up to view camera feeds. So the artificial horizon could be replaced with a window showing video feed for the operator to look at. And also the map. That is just an example map. It will not be a full map of the world. It will be zoomed in on a map showing the flight path. This is just an example. Moving on to security, there will be data encryption, which is encoding the data at the source and decoding it at the receiving system, and vice versa. There will be password protection and any other U.S. Coast Guard protocol that will be determined at a later time, as that information is not released to the public. Finally is launch and recovery. 2 operators will be used across the board for launch, flight, and recovery. For ground-based launch, the operators will assemble the system from the transport box and launch it. During flight, one operator will be monitoring the flight characteristics while the other one monitors the video feed. And upon landing, recovery, both operators will be disassembling and packing up all equipment and preparing for transport. For sea-based missions, the operators will set up both the system and the rail launch. During flight, both operators will be conducting the same jobs, monitoring the flight and video feed. And for water-based recovery, the operators will be needed to pilot a small Zodiac-style craft and pull the system out of the water to take it back to the Coast Guard cutter. The Zodiac-style craft is launched from the Coast Guard cutter, and it is large enough to hold both the system and the 2 human operators. Both operators will be needed to pilot this craft and pull it out of the water and take it back to the Coast Guard cutter. So in conclusion, the portable equipment consists of the ground station, rail system, and support equipment. The Autopilot system is how the human will interface with the system and control it. Security measures will be in place to protect the network and the data transmission. And for launch and recovery, 2 personnel will be needed. And for water recovery, a Zodiac-style craft will be used. Up next is Grace Brennan with cost and risk analysis.
Thank you, Stephen. The 3 costs Pelican Systems has analyzed are the cost of research, testing, design, and evaluation, the cost of production, and the cost of operations. For the research, testing, and design and evaluation part, we first determined the hours that were worked in both the detailed design phase and the preliminary design phase. The preliminary design phase is shown in red or black and was determined by the actual hours we have worked this past semester. The detailed phase in red was determined by the predicted hours from Professor Helding's previous classes. As you can see, one of the main differences is the detailed design phase has manufacturing hours. These hours were then multiplied by hourly rates also provided by Professor Helding to produce values of $109,000 and $134,000. We also included the actual cost of the wind tunnel model seen here and the projected cost of the flight test article. These values are $365 and $2,000 respectively. Total cost of research, design, testing, and evaluation is $246,000. For the production costs, we used cost estimate relations that depended on endurance, the weight of the payload, and the takeoff weight. These were determined in previous sections, and the results of the two cost estimating relations are averaged, and the result is $71,000. We also include the cost of the payload, the communication system, and the ground control station in the cost of production. These are then multiplied by the units required, which is 100 for all but the ground control station. And the result of this is around approximately $7,921,000. Of course, this is a conservative estimate because it does not account for the mass production savings. Part of the cost of operations includes the spare parts and accessories, some of these being the spare batteries, the battery chargers, and of course the rail launch system. The total for this is around $89,000. The other part of cost of operations is the cost of replacement. To determine this, we use the mean time between failure and the durability life determined in Bryce Silvertone's support section to find the number of replacements needed in a lifespan. These are then multiplied by the price of the component, which all results in a value of around $22,000. Adding these together, we get a total of around $61,000 for the cost of operations. In conclusion, the research, design, and testing and evaluation cost is approximately $246,000. The production cost is around $7,921,000, and the operation cost is around $61,000. This totals to an amount about approximately $8,277,000. This is, of course, for 100 units. And one of our future tasks is a wind tunnel testing, and to talk about the creation of the model is Jacob Powell.
Thank you, Grace. I would like to say that we have started fabrication of our wind tunnel model for our wind tunnel testing in the detail phase of the project next semester. I'll be going over briefly our wind tunnel model, our 3-view with dimensions, an exploded view, our model steel substructure, and a roasted view. Our scale is, we have a quarter scale relative to our aircraft that drives our platform area to be 136.5 inches squared with a wingspan of 35.9 inches. I was recommended by Professor Helbing to have our wingspan to be no more than 36 inches to avoid wall effects of the wind tunnel. We are currently predicted to be under 5% solid blockage of the wind tunnel at 60 degrees angle of attack. And our maximum predicted wind tunnel speed is 179 feet per second. As you can see here, our wing, as previously stated, is 3 feet. Our overall length of the aircraft is 18.5 inches, and the height of the aircraft with the base is 5.28 inches. Here's our we developed 10 ABS parts using a 3D printer. As you can see here, we have our wings that will clamp together with our fuselage. And in the next slide, you see those will attach to our seal internal mount, which has already been fabricated in our fabrication lab. The seal substructure is designed to carry all the loads of the aerodynamic of the wind tunnel model. And as you can see here, the tail booms will slide over our wing spars, thus transferring that load into the steel substructure and not into our 3D printed parts. So, in conclusion, as you can see here, we have 10 3D printed parts. We have 11 steel parts. We are predicted to meet we're going to meet the solid blockage of less than 5%. We have a determined wind speed of 179 feet per second. Also, I'd like to mention further sanding and epoxy will go on the model, as well as a single layer of carbon fiber onto the wing to prevent flexure during testing. Next is Salvador Cardenas with project management.
Thank you, Jacob. So I'll go over our labor hours first. And as you can see, we have 5 categories: engineering management, engineering, technical, administrative, and professional development. And we have a total hours to date of 2,361. So here we can see it visualized on a pie chart. As you can see, most of our time is spent in professional development and administrative, which included making presentations, writing up our reports, and et cetera, et cetera. And then, of course, engineering was our third, which consisted of setting up our CATIA models, our spreadsheets, all the initial setups. And here we can see a plot of our predicted hours versus our actual hours. The red line is predicted, and the blue line is actual. As you can see, we started out with a slow rate and slowly increased to the same pace as the predicted hours, but with less magnitude. And here's, in conclusion, here's our requirements that we're predicted to meet. And of course, we haven't met our ground rule for landing, which we need to look into. And we still don't know if we're cost effective or if we can disassemble or assemble the actual flight test article. And some of our limitations would be to waterproof our cooling vents for the sea-based mission, and landing and decrease our landing ground rule, which we would look into spoilers or flaperons to decrease that distance, and also to improve our sea-based landing to avoid the propeller from actually hitting the water. So we would look into orientating the propeller horizontally to avoid that. And our future task would be in detail design to actually do our wind tunnel testing and prep our model for wind tunnel testing, and also structural design and testing of the actual aircraft and building the flight article and testing the land-based prototype next semester. And I would like to acknowledge all the panel for taking the time to listen to our presentation, and all these professors who have helped us and put their suggestions into our project. And of course, Patrick David, our machinist, and Patrick Deskin, who helped us print and manufacture our parts. Thank you very much, and any questions?
We're going to start with a lot of information included. Appreciate that. Specifically appreciated all the disclaimers about these are assumptions, we'll get to it later. Point proven. How is ground-based steering accomplished on this vehicle?
We haven't looked into that, but we were thinking of using an actuator mounted internally to actually perform training.
Okay.
Yeah.
Do you have braking capability?
No, we don't.
Okay. That's what makes your landing distances so much higher too, right?
Right. So, and we didn't want to increase our weight, so that's why we can't use brakes.
Sure. That could end up being an option for you to provide your steering capability through differential braking or what you actually need to meet that requirement. It's an option. You do trade for weight and complexity. Absolutely.
Right.
Talking a little bit about the configuration in the sea with the pontoons and vertical spacing over the water and deck angles. You're rail launching it, but in any of the configurations, are you going to be dragging your tail on the water?
We might for the sea base, so that's why we're trying to look into orientating our propeller horizontally when we stop the motor and power off to land in the sea. So that's our vertical is actually, I think, 3 point. I'm not too sure about the number right now, but it's in the slides. It's in our backup slides.
Okay. I have one more. Oh, elevator sizing, and kind of a similar thing there. You size the elevator specifically for the rotation condition on takeoff on a land-based configuration. You also give yourself some benefit by setting an incidence angle on the ground through your landing gear arrangement. Your CG in that sea-based configuration is further forward than your land-based configuration, which will make your airplane a little stiffer in pitch than the land configuration. Did you at least check your pitch authority in both land and sea configurations? Only in the land-based configuration, we have it set up so the battery, we can shift the battery so we can keep our center of gravity in the same location. And for the maximums of inertia, the land-based ones are greater because of the landing gear. So right now, we have not. Our elevator is currently a little oversized based on thrust and engine power, the thrust the engine's producing, along with the friction from the ground roll. So we were having trouble in the past, so we made our elevator as large as we could. Now, after going through some more iterations, we're capable of rotating with much less elevator authority than we initially were. So our elevator is currently oversized, and that's going to be something we're going to look at into resizing after we get more data from the wind tunnel testing. Okay, great, thanks, good work.
Good job. I had a couple things. Starting on page 3, you didn't, there's a rail launch requirement. And throughout the whole thing, you're talking about takeoff from a gravel runway. My gut just tells me taking off from a gravel runway is a requirement that you need to challenge. You need to tell the customer, it's stupid. I have to build this into a rail launch. Let me do that from land too. I then can have a synergistic solution. I don't have to have brakes. I use a landing skid like Spaceship One for the nose. I get better aerodynamics because I could pull that up if I really wanted to. There's a lot of things that you could play if you challenge that one requirement. So I think that
we did challenge it. This
Okay.
is a flight test article. We aren't actually going to buy a rail system, and they aren't actually going to let us land on Willow Lake. They said we still have to be able to take off the gravel runway.
Okay.
So we did challenge it.
Okay, good. Great.
They didn't tell me I was stupid.
We generally try to couch it a little more politically correct.
Thank you. When's your turn?
There's just a lot of places where I think you could really make some cost-effective improvements. The wing taper, great for aerodynamics, but it's costing you a lot. So see if there are ways you can challenge some of the shaping to get manufacturing costs down, operating costs down. There was a comment of 179 feet per second for your wind tunnel test. I don't understand what you're telling me with that number.
It's as fast as we can run the wind tunnel without going over the 40-pound limit of the platform.
Okay. But how fast is your airplane to fly?
30 knots.
So, yeah, so 179 feet per second is way, way above.
With 179 feet per second, that gives us a grounds number of 400,000. Our aircraft roughly flies at that. It's a little under. It's about 380,000. So we definitely we don't have to go as fast as that, but we want to try to achieve models similar to it.
Yeah, I just don't know that the change due to Reynolds number is very steep in that range. So dynamic similitude may not be that important in that Reynolds number region.
Okay.
So just something to think about there. Just the way the layout of the top, some of the design envelope stuff to me would have been better ahead of the details on the avionics. It's just the way I think. I'm an airplane fan. And I think there's some of the comments about your airborne antennas. You want real airborne antennas. And some of those look like they may not be a good choice. But
What do you mean real airborne antennas? Like blade style?
either blade or flush mount or something?
I might have not mentioned it, but they were supposed to be mounted internally.
Okay, all right, that helps. And then you had, page 72, you had some information about the, so you said that was a first order analysis?
It was a 1 degree of freedom estimation provided by Raymer. We made a simple model of 1 degree of freedom.
I just don't trust me, Dan. Don't ever trust Dan. I would have really liked to have seen you show me your inertia and its effect and your control power, so I could have actually seen a second order response characteristic here. That I think in Simulink that would have been a no-brainer for what you already had done. So I think that would have been a nice touch. Don't go on Anthony's, I worked with him too long. The same with Nikolai and all the designers. I always question what the designer tells you. You're the best bet. I think that was the short period. Go back and reanalyze the short period too. I just gut check that something was wrong. I kind of expected spiral to be slightly unstable, and I expected the short period with 15% static margin to be nice and stable. So just gut check there.
We'll reevaluate that later.
Okay.
Yeah,
Great.
that looks pretty okay.
Yeah. Great job.
Yeah, very nice. Well-organized presentation, nice transitions between each team member, cover a lot of material in a short amount of time. I'd say good choice on the motor, 5 horsepower. One thing that I've seen repeated in the past is you always surprise yourself how much power you need, so that's good that you're overpowered at this point. Let's see, I've got well, let me make a general comment. You're essentially designing one airplane to accomplish 2 missions, and that is a very challenging thing. And so you have to keep on going back and making sure that if the assumptions that you make for one mission are reasonable for the other mission. Like for instance, I'm looking at the airplane sitting on the table there, and with the landing gear on there, it looks just fine. But if I take the landing gear off and put pontoons on there, I can immediately envision dragging a wingtip in the water and probably causing pretty significant damage to your airplane. Maybe a little bit of hedral, or maybe your pontoons could be a little taller to prevent that. But it looks like there's actually some anhedral to that configuration, and that might not be the.
I think that's from
plastic.
Yeah, plastic.
Okay. But even if it were flat, I can imagine dragging a wingtip. Kind of along that same line, when I looked, I saw the moment of inertia calculations. I only saw one set of moments of inertia. And when you're doing your analysis, you really need to check it for both sets, because that could surprise you when you change, when you do the moments of inertia calculation for the 2 configurations. And you just need to analyze it both ways. I gave the previous team the same comment. I think your wing and empennage thicknesses are too thin with one layer. From a durability perspective, I've seen small airplanes, just by virtue of picking them up and ground operations and handling them, you can end up damaging your vehicle. So you need to consider that. Pretty small UAVs in particular, because there's a lot of hands-on activity, and your airplane may not last as long as you want it to, especially with composite. If it were something else like the shrink plastic that you use on model airplanes, it's easy to repair. That's one thing, but with composite, it's
going to be kind of a challenge. Another thing to think about for your water operations is waterproofing your aero surfaces. I can imagine you getting a lot of moisture, even getting them waterlogged for water operations. Getting onto the, I think at one point I saw there were 4 antennas on the airplane and they're all at 2.4 gigahertz, is that correct?
Yeah, it's 2 on the ground, 2 in the aircraft.
Okay, 2 on the ground, 2 on the aircraft.
They all work on frequency hopping megahertz band.
Okay, good. And let's see. I'm not a stress guy, but let me go to page 89. To me, that looks like the point at which the load is applied to where the axle is in the wrong spot according to that stress analysis, but that's just me. And maybe it's not accounted for at the top either.
The way I set it up is I have a fixed support at the top where you see all those stress concentrations. And at these, where the rod goes through, I put 2 loads, just like that way.
Okay. Again, I'm not a stress guy, so that's probably a reasonable thing. And then one other thing too, go to page 63. And that looks to me like your axes for that particular aircraft are assuming an airplane that's at some positive angle of attack. Then go to page 64. And that one looks like it's more or less in alignment with the fuselage. And then go to page 70. Again, that looks like it's in alignment with some coordinate system that's not on the center line of the vehicle. I'm not sure what your actual coordinate system orientation is, but as a team, you want to pick a coordinate system and make it something that's easily referenced on the vehicle itself. Along the center line is probably the best, because at some point you're going to want to take a tape measure and measure various points so that you can place components and that sort of thing. And you want a reference point that's easy to access. And coordinate systems can be nightmares. I've seen dozens of coordinate systems on different vehicles, and it's a challenge to keep track of that. So if you could pick an easy one that everybody can agree to early on, that's best. But nice job, nice presentation.
Shall I thank our panelists again, please?